Question 33 says, which of the following, the four fundamental forces, is both repulsive and attractive? Okay, most of the forces are only attractive. They tend to attract. One of them happens to be one that attracts and repels. So which one is that? Well, I think most of you already know this. If you have two minus charges or two plus charges, what do? They repel each other, right? And if you have a minus charge and a plus charge, they attract each other. So the electromagnetic force is attractive and repulsive. The weak nuclear force, strong nuclear force, gravity, they are all attractive. So it's choice A. That is both attractive and repulsive. Now, what are the other properties of these forces? Well, if we write them out, strong nuclear force, electromagnetic force, weak nuclear force, and gravity, one of the properties that we could write down is their relative strength. Okay? Relative strength. If we call the strong nuclear force 1, that's how strong the strong nuclear force is, the electromagnetic force would be 10 to the minus 2. Well, what does that mean? Well, roughly on the order of 100th. It's 100th as strong as the strong nuclear force. Okay? So, roughly speaking, if you were to argue, okay, you have this atom here, and imagine the nucleus of the atom. Imagine you have protons, proton, 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 neutron, 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 right? These protons don't like each other, right? They're repelling each other. What's keeping them intact? What's keeping them from breaking out of the nucleus? Well, the strong nuclear force has a strength of 1. The electromagnetic force is 100th. So the electromagnetic repulsion of the protons is compensated by the attraction of the strong nuclear force, which is 100 times stronger. So this and this, 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 they're binding each other with the strong nuclear force, with a force 100 times stronger than the repulsive force among the protons. Well, that's going to be sufficient to keep the nucleus intact, even though there are so many protons that are repelling each other, right? How about the weak nuclear force? The weak nuclear force is 10 to the minus 6, okay? The weak nuclear force does not have to be that strong. It's 1/1,000,000th the strength of the strong nuclear force. The weak nuclear force mediates radioactive reactions. Gravity is very, very weak. It's 10 to the minus 43. 10 to the minus 43 times as strong as the strong nuclear force. So if you compare it to the electromagnetic force, it's about 10 to the 40th. 10 to the 40th weaker than the electromagnetic force. So on the scale of the atom, on the atomic scale, gravity doesn't really do much at all. Gravity is only noticeable on the vast, giant scale of planets, and gravity is what is responsible for forming stars and for stellar explosions, supernova, and all of those kind of things. On the atomic quantum scale, gravity is almost meaningless, so it's almost non-existent. So the gravity is only important in the large scale of the universe. The other kind of property that we can write here is, besides relative strength, we can write range of the force. Range. Okay, so what is the range of the strong nuclear force? It is very short, of the order of 1 femtometer. Okay, 1 femtometer is 10 to the minus 15 meter. Well, that means the range of the strong nuclear force is only within the nucleus of the atom. The nucleus of the atom is of the order of 10 to the minus 15 meters, so the strong nuclear force has a very short range. The electromagnetic force is long, very long. Okay? Objects that are almost infinitely far away can still attract or repel each other. And the range of the force is 1 over r squared. Okay, so we learn in electromagnetism that the electromagnetic force goes as K Q1 Q2 over R squared, so it is proportional to the distance squared of the charges from each other. Okay, what is the range of the weak nuclear force? This one also happens to be very short, only within nuclear distances, about 10 to the minus 3 femtometer. 10 to the minus 3 femtometer. So again, within the distance of the nucleus. Gravity is long range. Long range. Well, that we know. I mean, stars that are infinitely or far away can still attract each other. The force will be negligible, but gravity can still penetrate very, very far away. And the proportionality is 1 over r squared as well, just like the electromagnetic forces. So you have 2 long-range forces, 2 short-range forces, okay? Besides that, we could also write down the mediating particle, what particles mediate these, but we've already written those on previous videos, right? I'll just mention them quickly. The strong nuclear force is the gluon. The electromagnetic force is the photon. The short range weak nuclear force is the W plus minus and the Z bosons, okay, and gravity is the graviton, okay. Hopefully in the upcoming future we will have a better understanding of these particles and all of these vast array of things that we have been talking about through the understanding of string theory, okay. So now you can see which of the 4 fundamental forces is both repulsive and attractive. We could have had other questions. We could have said, which of the following forces is the shortest range force? Well, shortest range would be the weak nuclear force. You could have said, which of the following 4 fundamental forces is the weakest force? Weakest force would have been gravity. So you could have had different kinds of questions on this chart by itself. Okay? Thank you very much.